Now, the authors in the next section of the book, this is now section 5.6, if I remember correctly. Let me just quickly go there. Yes, they make the, oh yeah, it's even on the slide. I should just have opened my eyes. They make the case that the PI controller is a special case of a phase lag compensator. Now, we have learned about the PI controllers briefly in chapter 7 when we talked about root locus diagrams, but it's also introduced in equation 1049. Well, at least equation 1049 is just this first part of this equation, the one in the rectangular block. But I can, of course, quite easily show by putting the two terms on a common denominator that that my PI controller is KPS plus KI over S. And then I can factor out the gain KP and put it in front of the fraction, which will leave me with a denominator of S plus KI over KP over S. And if we now compare this to the definition of the lag compensator that we use, that we've seen on the previous slides, we see that it's really the same for the special case where P is equal to 0. 1 over alpha can be then compared to the KP, and of course the ratio of the integral gain to the proportional gain, Ki over Kp, that is simply your 0 location. In terms of figure 10.7, figure 10.7 you will recall is the general diagram showing the pole locations of the pole and the 0 of a lag compensator. So this is a general graph. So it means that the PI controller will be a graph like this with just this one difference, or with one special feature, namely that the pole is really right at the origin. So instead of indicated here, it's as indicated with a red cross. So what we see is that you can think of the PI controller as the limiting case of a lag compensator. On the one extreme, if the pole is located right at the 0, that is a PI controller. So therefore we can conclude that all PI controllers are lag compensators, but certainly not all lag compensators are PI controllers. In other words, if I have a lag compensator where the pole of the lag compensator is not at the origin, of course, in that case I can still say it's a lag compensator, but it's certainly not a PI controller. Now, what is not in the book, but something that I'd like to just bring to your attention, is that the practical PD controller can be seen as the limiting case of a lead compensator. It's not discussed, as I've said, but to just see a little bit more about the PD controller, I'd like to refer you back to section 7.6 on page 503. And of course, the PD and the PI controllers are not specifically discussed, just the PID, but you can very easily derive a PI from a PID by just making the differential gain K sub D 0. And likewise, you can get a PD controller from a PID controller by simply making the integral gain Ki equal to 0. Now, if we do the latter, if we make the integral gain 0, and we take note of the fact that the practical PD or a PID controller cannot just have S in the denominator, as indicated on page 503, there must be a high frequency pole to make it practical. Otherwise, you have an improper transfer function for the compensator, for the PD controller, or even for the PID controller. It will be improper if it only has a single pole, a single S in the denominator, a single pole. There must be, to have a proper transfer function, there must also be a high frequency pole. And that is represented right at the bottom. It's briefly discussed right at the bottom of page 503 by indicating tau sub ds. This is the time constant of this high frequency pole is tau sub d. And this tau sub d is a very small number. In other words, the time constant of the pole is very small, which means that the pole sits at a very high frequency very far to the left on the real axis of the S-plane. So we can say that the time constant of this pole is much, much smaller than, and that is what they say on page 503, it's much, much smaller than the time constants of the dynamics of the system that you'd like to control, which is really the same as saying that it's much, much smaller as the ratio of KD over KP, which we have in the numerator, and which really defines the zero that is associated with my PD controller. So if we then look at a practical PD controller as we have it here, we can see that we can factor out the KD in the numerator once again, and then we can put that in front of the fraction, and then the numerator will reduce to S plus KP over KD, and of course the denominator stays the same, tau ds plus 1. And if we now compare this to the design definition of the lead compensator, we see that we really have the same, where the zero is at the value Kp over Kd, and of course where the pole P just becomes very large. The pole P is really the reciprocal of 1 over tau d, and you can think of it as that P goes to infinity or becomes very large. So with this then we can say that a PD compensator, that the PD compensator is a special case of a phase lead compensator. Not all PD, so we can say all PD controllers are actually in the limit phase lead compensators. All practical PD controllers, at least, can certainly be said are phase lead compensators. Of course, not all phase lead compensators are PD controllers. That we cannot claim. In other words, if the pole is located infinitely far or very far to the left at a very large value compared to the zero, then we can say we have a PD controller. Now, the general trends that are associated with the phase lead and the phase lag compensators are summarized in table 10.7 right at the back of chapter 10. Now, I must admit that the table is a little bit confusing. It's not to be disputed what is mentioned in the table, but you can argue that all the properties that are heaped on for the praise of one of these compensators, if you look at the design procedures, you can say, well, the other compensator can actually do the same. And that really makes it a little bit difficult to decide when will I design a phase lead compensator or when will I design a phase lag compensator, because I can really do the same, generally speaking, with either of them. There are however two properties that are really quite different between the two compensators. And that is that the phase lead compensator increases the bandwidth of the closed loop system, whereas the phase lag compensator decreases the bandwidth. Now that is really the same. So even though I've listed it here as two properties, it's really actually the same property. Increasing the bandwidth really means that you speed up the response of the system. And decreasing the bandwidth means that you slow down the response of the system. Now, you may perhaps immediately ask, well, why would I like to slow down the response? The answer to that is sometimes when a control system operates in a noisy environment, you do not want to have a too high bandwidth, because if your bandwidth is in fact high, the noise in the system actually gets amplified and it makes the control very difficult. So in a noisy environment, quite often you may find that you have a bandwidth limitation. It may be specified in the specification that the bandwidth may not exceed a certain frequency. And if you have such a bandwidth limitation in the specification, you should be very careful to design a phase lead compensator. Of course, you can perhaps try to design a phase lead compensator, but after you've designed the phase lead compensator, you must just make sure that the phase lead compensator that you intend to use does not in fact push the closed loop system bandwidth over the band limit that is specified. So if you, at the beginning of your design procedure, check the bandwidth, and the bandwidth of the uncompensated system is already very close to the specified bandwidth limit, or is even higher than that, in that case, I will certainly not try to use a phase lead compensator. And of course, the same applies for the PD controller then, because the PD controller is a special case of the phase lead compensator. If there's a bandwidth specification and the uncompensated system is already close to it or over it, certainly not a phase lead compensator. On the other hand, if there's no bandwidth limitations in the specification and you want to make your system faster, in that case, the PD controller or the phase lead compensator is a good choice. Having said that, also bear in mind then that the phase lag compensator or the PI controller tends to slow down the response. And this can then be an advantage, but usually it's considered to be a disadvantage.